The focus of this video is to introduce geometric proofs, but we're going to start first with what we're a little bit more familiar with, which is algebra, and then break down just one line of a proof, and then finally enter into beginnings of geometric proofs. Before we can begin, let's talk about the layout of a proof. So all proofs are set up in two columns. So there's usually a line down the middle, and then a line at the top separating your statements from your reasons, okay? Your statements are usually your mathematical statements. And I want you to think about it as almost like directions to your house or the directions of a recipe. There's, it's very systematic and step by step. You can't really skip steps. If you skip steps in a recipe or on your directions, you're going to end up in the wrong place or with a very gross tasting thing. So this has to be very systematic and step by step, no skipping. Your reason section is pretty much straightforward, but this is usually where your definitions, your theorems, and your postulates are located. And essentially the reason that those are there is because these reasons are what we have to say right next to what we said. So like, I'm going to tell you to do this, and this is why I'm going to tell you to do it. So essentially but it's not in paragraph form. It's very much in list form. So that's kind of the basic setup. So before we can get to geometric, let's start with something that you might be a little bit more comfortable with, which is algebra proofs. So you can see that two-column idea is present. Here is your statement and your reason breakdown. Everything on the left is not always given to you. Sometimes, in very advanced proofs, there's literally this whole thing is blank, and a student would have to fill in the entire thing from start to finish. Other times, there's bits and pieces of it are there, and you have to fill in the missing parts. That's really the requirement that we're going to ask you, is to fill in the missing parts. But let's kind of work our way up. Every single proof is set up in the same way. There is always a given statement, and there is always a proof statement. Not only are those two things present, but where they go also is an expected thing. The given statement will always be your first line, and your proof statement will always be your last line. That's pretty much a guaranteed fact. Sometimes the given statement can take up multiple lines. Sometimes the given statement can all be given, like every single piece of information can be given in line one. That really is dependent on who's writing it. Okay, so once we get the basic setup, right, we know line one and the last line are pretty much a solid whatever we were given. We have to talk about the reasons why in this case. So I look across here and I think, well, why can I say the thing that I've been given, or that they stated here? And the reason is because I was given that statement. So this top reason, usually always not like a locked in, it's given, okay? After that, you have to kind of systematically think about how I can go from step one to step two. When you're given that, like when both statements are given, you really have to figure out what's the reason that I can go from here to here. In algebra, it's what step happened. So if I look at the connection between the two, well, I can see that the -9s are both still present and the +6s are both still present. So it means something happened with the x's. In this case, we could argue that the 10 was subtracted because the x ended up on the right side of the equal sign. So this is, I'm able to say the second line because of the subtraction property. After that, we do the same exact thing, but now we're asking ourselves, well, how did we get from step 2 to step 3? The two x's are still there, which means that we did something with the constants, with the numbers. So again, in this case, to move the 6 over, I did the subtraction property. Continuing this process, we look at how we got from step 3 to step 4, and this is the division property. And then this last step is a little bit picky, but we're going to talk about it just in case it ever pops up. But even though this looks like you've done it, right? In algebra, this would be enough. In geometric proofs, it's not. because they have to be, the order matters, and it has to be written exactly like it is here. So when this happens, there is a property on your notes that you did today called the symmetric property, which allows you to flip the side that it's on. So essentially we just reversed the order, so it's in the exact order that we were given. So this is a finished proof. We have all of our statements that are filled out. We got from the proof state or the given statement to what we were trying to prove, and we have the reasons filled out on the right. All right, let's try one more of those just to make sure we're good. Again, note that your given is step 1, and what we're proving is step 5. So why are we able to say line 1? Again, because it was given. When we look at what happened between step 1 and step 2, the only difference that I see is this side of the equation, and the way we got that is by doing this property here, which is the distributive property. From there, it looks like there's a connection between the 5s and the negative 3s, which means that something happened with the 3x. And the only way I could move this over is by subtraction. So this is the subtraction property. From there, from line 3 to line 4, I would have moved the 3, it looks like, to get 8. So this is the addition property. And last but not least, divide by 12 to get 2/3. So this is the division property. No symmetric property needed here because the x is in the exact place that it's supposed to be based on the proof statement. All right, so this is kind of the end of algebra proofs. So what I'd like you to do is to push pause on the video and go through the following 2 examples of algebra proofs and just get yourself kind of used to that systematic approach. When you're ready, come back to this video and push play, and we'll continue on. Welcome back. At this point, we are going to start beginning the idea of geometric proofs. And before we really jump into all out geometric proofs, we wanted you to get practice of picking out that why, that reason, and then also picking out a conclusion to draw, that next one, not skipping steps. What's the next thing you can say, and then why can you say it? So we kind of broke this down, and so you'll see on the next page of your packet once you get there that we have lots of these different types of examples. So this first example already gives you the given, and it gives you the statement that we could have said. The question is why. So why am I able to say on line segment CT, so here's C and here's T, if A bisects it, why am I able to say that CA is congruent to AT? And so you can't go well, the picture said it, or I just know. None of that actually works, right? So you have to go back to what we were given. So what part of that statement allowed me to say this? And they're really, A doesn't tell you anything, and line segment CT doesn't tell you anything. So the only thing that really we can attack is the definition of bisect. You can also say bisector. I just put either one's fine. But this is the only thing that told us that these 2 parts are going to be congruent. So just kind of something to consider there. Think about what you can attack, and what you actually know, don't assume. For the next one, we are given this picture. So I can kind of see this happening multiple ways. Miss Felicity, who did the answer key for this, saw this a different way than I did. So I'm going to show both because I think both are accurate and both work. So Miss Felicity saw this picture, and she went right to angle 6 plus angle 7 is equal to 180 degrees. This is exactly what your answer key says on your document that you have. And she wrote the linear pair postulate. Whereas I would have actually broken this into 2 steps, right? So based on this picture alone, I'm sorry, not 7. I'm sure. Sorry, this is a 5. Ooh, did I do 2 different ones? No, we're good. Okay. So I would have actually broken this down into angle 6 and angle 5 are a linear pair. That would have been my conclusion 1. And my justification would have been the definition of a linear pair. And then I would have been able to say angle 6 plus angle 5 equals 180. Oh my gosh, I wrote a 7 again. Angle 6 plus angle 5 is 180 degrees. And then I would have used the definition of supplementary. So I can see this happening both ways. Just kind of knowing how you want to go about that is important. And also, like, you're going to be given bits and pieces of proof, so kind of get a knack for like what the flow is or what they're asking. One thing to consider is there is a little bit of freedom in these proofs, but when they're kind of filled in, there isn't. The other thing that I kind of sense from students that they get really annoyed by is like, this is so weird. I said it and then I wrote the same thing. This seems really useless. It might be. But sometimes this is just kind of the situation that we're dealt. So almost a little bit of suck it up buttercup here when you have to kind of do that. That's kind of the structure of how it works. Okay, so this part can be a little bit confusing, but I want you to give it your best try. There's 8 examples of each, now 7 because I did 1 of each, but 8 examples of each on your picture or on your packet. I want you to give them a try. The answers are included. If you are really struggling with this part, this might be an indication that you should maybe grab a nucleus pass today, come in and either work with Miss Felicity or myself to try to get some help because it's not going to go away. Okay, so we got to kind of fix or help where we can. All right, so at this point, I want you to push pause and give that a try. All right, welcome back to this video. We're ready to jump into geometric proofs, which is what you can see right here in front of you. This is an example of something where we have bits and pieces of this put together for you. I feel as if we continue to move forward, we're going to take more and more away. But for right now, this is the safe place and this is where we're going to be. Okay, so you can see that basic structure is still there. Our given is here and it shows up right here in line 1. Our proof statement, which is below that, is right here. And that, remember, needs to be down here. So before I even start this proof, I can kind of fill in what I already know. Remember that the reason why I can say that first thing is because it was given. All of our proofs will have word banks for you. There'll always be way more options than you need. So you kind of have to figure out what you need and what you don't need. Okay, I also can say the last line. So the measure of ABC is equal to the measure of DEF. And I guess I can say that because of substitution. So I already have 2 of these blanks already filled in based on the basic setup of proofs. So now we have to kind of get to the nuts and bolts. So the first thing I would consider is like, what was I even given and what does it even mean? So I was given that angle 3 is equal to angle 4. And I was also given that angle 1 is equal to angle 2. So that's where I'm trying, I guess I should also do, I'm trying to prove that this larger angle is equal to this larger angle. So that's my end goal. Okay, so looking at what I've been given, I was given that angle 1, this angle right here, plus this angle right here is equal to something. And it's by the angle addition postulate. So if you're not sure, you should go read angle addition postulate. But it's really just talking about how 2 smaller angles that are adjacent can add up to the larger angle. So the larger angle is the measure of angle ABC. And when we put the measure in front, we're talking about it's just saying it's a value. Okay, so we're not using congruency, we're using equality right now. So that's just something to keep in mind that we're using measure because we're talking about, we actually mean the numbers. Okay, so measure of ABC was right here. There should be a space there. I apologize. I think I fixed it for your paper though. All right, now the next line. I have to do something equals DEF. So I'm thinking that it's kind of similar to the last one. So the measure of angle 2 plus the measure of angle 4 is equal to DEF. That just looks terrible. All right, and I'm going to steal my reason from above, the angle addition postulate again. So now I really have to figure out how I got here. When you take a look at this, or when you try to break this down, you can notice that there's some similarities here, right? So it's like I took this part right here and I equaled it to this part right here. And the only way we're able to do that is based on what we were given before. If I know that 2, so if I know that this angle right here is the same thing as this angle right here, I could just interchange these. Same thing with 3 and 4. I highlighted in the same color because they're equal, which means I can interchange these. So I believe that the reason we're able to say 4 plus 2 is ABC is because of substitution. I substituted out the angles and put in something that is equal to them. And therefore, again, I can do the same thing with the next two, right, with the last line, because these two end up being equal, but it's because these two were equal. So substitution kind of finishes that proof out. This can feel kind of awkward at the beginning. It could click, it could not. These can be very difficult. So please, if you were like, oh my gosh, that was really hard, the more you do them, the better you'll get. All right, let's try one more, and then we're going to kind of release you to try some on your own. So using the basic setup of what I know about a proof, I'm actually going to start my proof off with angle 1 and angle 2 are complementary. And that's because it was right there in the given. I'm also going to finish this proof as well. Ray XA is perpendicular to ray XC. I'm going to finish that as well. So I'm going to give myself a little bit of a break and kind of get some of those blinds and blanks taken care of. Okay, so now I just need to actually think about what this proof is even about and what I've been given. So knowing that angle 1 and angle 2 are complementary, I should read the definition of complementary, which after you refresh your memory means 90 degrees. So which weirdly is exactly what the next line says. It says, well, that means that angle 1 plus angle 2 is 90 degrees. Well, the reason I knew that is because I went to my notes and I checked out that definition. So definition of complementary angles must be the reason why I can say this. Sorry about my spelling here. Okay, so the measure of angle 1 plus the measure of angle 2 equals something. And I'm using that angle addition postulate again. Well, remember, that's two smaller angles add to the larger. So I think this is going to be the measure of the larger angle, which is AXC, which is also on my list there. So now they're saying the measure of AXC is equal to 90. Well, looking ahead, y'all look at this. We said the same thing twice, but we equaled it to two different things. So this could be, I could see this kind of being two things, but I'm going to go with substitution. So you could say substitution here. I'm going to also argue that there are some students or some people that would say the transitive property. So I really want to talk about why this is more substitution and not the transitive property. So when you use the transitive property, you're using this with like angles, segments, lines, like you're talking about geometric things. So the actual property says if AB is equal to BC, then, and BC is equal to CD, then AB is equal to CD. Okay, so there's all this stuff, right? So essentially, if these two are equal, then these two have to be equal, or whatever. So when you're dealing with lines, transitive property is the way to go. When you're dealing with numbers, okay, which we are because we have this measure of an angle right now, that measurement means we're dealing with numbers. You want to use substitution, okay? When you're dealing with algebra, you want to use substitution. So this is not the transitive property because of the fact that we're dealing with numbers, measure. All right, at that point, we could then say because we know that 90-degree angles are perpendicular lines, we can say that these two rays, XA and XC, are perpendicular because of the definition of perpendicular lines. All right, so this brings us to the end of this video. There are a few geometric proofs that we'd like you to try on your own. The answers are included as well. Please don't flip to the back and just write down those things. Really try to break them down and see if you can figure it out. And if they don't match, the next question you should be asking yourself is why don't they match? That's going to be really, really important. What do you need to do to fix it? That's the important question, okay? Work together if you need to. And again, if you are struggling with this, please, please, please come ask us or come get a nucleus pass and work with us. We are here. Miss Felicity and myself are here to help.